Hello everyone, and today we are going to talk about addition of matrices. Let's take a matrix called A, and let's say I denote these entries like this, that is 1, 2, 3 and 4. And let's take another matrix of the same order, and let's denote these matrices, the matrix elements as 0, 1, 1 and 0. So I want to evaluate what is A plus B. To do that, we write A plus B equals 1, 2, 3, 4 plus 0, 1, 1, 0. Now, how do we add them? We have to add them element wise. I mean that this is 1 appearing in the first row and the first column, and this is a 0 appearing at the first row and first column. So first we have to add these two, and 2 here will be added to this one. Similarly, 3 will be added to this one, and 4 will be added to this 0. So if I write it down explicitly, I'll have 1 plus 0, 2 plus 1, 3 plus 1 and 4 plus 0, and just add them, add these numbers, and you get 1, 3, 4, 4. This is our result for the matrix addition. Now let's take a look at another example. This time we will be taking a column matrix 1, 2, 3, let's say, and another one. Let's give it a prime so that we don't confuse ourselves, and let's say 0, 1, 1, and A prime plus B prime will be given by 1, 2, 3 plus 0, 1, 1, and you can readily evaluate this as 1, and 2 plus 1 is 3, 3 plus 1 is 4. So the general rule, that is, if you have a matrix A and another matrix B, then element wise, or let's say when you want to write them as components, we have to add them in the following manner. That is, A plus B, let's say this is the resultant matrix that comes from A plus B, and let's call it C first. And if I just go a bit down so that I can have more space, so we wrote C equals to A plus B, right? But this is a matrix, and these A and B's are also matrices. So what we can do, we can ask the following question: what is C of ij in terms of A plus B? It turns out that C of ij is just A of ij plus B of ij. That means you have to add the matrices component wise, or say element wise, whichever way you like. And the explicit examples that we saw here and here reflects this fact, that is this one. Now let's talk about how can we multiply a scalar with a matrix, that is scalar multiplication. Scalar multiplication. So again, let's take a scalar, let's say A equals to 3. This is just a number. And let's say you have another capital A. Okay, let's not denote it by capital A. Let's denote it by Z, capital Z. And this is a square matrix, let's say 1 2 0 0, and I want to evaluate what is A times C. So the answer is, you just type 3 here, then you write this matrix out, then you need to multiply this 3 with each of these matrix elements. That is, you multiply 3 with 1, 3 with 2, 3 with 0, and then 3 with this 0. So the result becomes 3 6 0 0. That is the idea for scalar multiplication of matrices. Let's take another example, just so that we are clear on matrix multiplication with a scalar. Now let's take a column. No, we have dealt with column matrices before, so let's take a row matrix right now. Let's call it B, and let's say it's 1 1 0, and we want to multiply 5B. We want to evaluate what is 5B. Just type 5 1 1 0 and multiply 5 with every element. There you go. So this is how we can scalar multiply a matrix. And now let's talk about some properties of addition of matrices. That is, we want to talk about some properties. Let me use another color, green, let's say. Properties of addition and scalar multiplication. So the first property that we are going to see is that if A and B are two matrices of the same order, remember they have to be of the same order, otherwise we won't be able to add them. Then A plus B equals to B plus A. This is called commutativity. That is, addition is commutative. So let's write it like that. Okay, let's just write it as addition is commutative. By commutative, we mean that the order in which these matrices are added does not matter. That means whatever the result A plus B will give us, the same result will be given by B plus A. How can we prove that? The easiest way to prove it is to work in the component notation, or sometimes called the index notation. So from now on I'll be calling this the index notation. So let's say Aij is some element of A. This epsilon here denotes the belongs to, that Aij belongs to A, and Bij belongs to B. And note that A and B, these are just numbers. Now if we write A plus B and we want to check its component, that is on the ith row and jth column, then we have to write it like Aij plus Bij, right? But these are just numbers. It's like adding 2 plus 3, and you get the same result when you do 3 plus 2. So you can write it as Bij, Aij, right? And from here you can write B plus A, Ij. That's it. Very simple. The second property that we're going to see is the associativity property. That is, the second property is associativity. So we say matrix addition is associative. What do we mean by that? Let's say A plus B. We have to add these two first, and then I add another matrix called C. Again, A, B and C have the same order, otherwise they are not going, otherwise the addition doesn't make sense. And this is the same as A plus B and C, which means add B and C together first, then add A. And the left hand side tells us that A and B are added first, then C was added. And from here you can actually see that these brackets doesn't matter. That's what associativity is. That's how the mnemonic goes, that the brackets don't matter. Again, you can prove it by the similar method that is shown here. That is, you just write out the components and you just shuffle them, and that is it. So this is the associativity. Next property we want to see is about scalar multiplication. That is, if you have two scalars, let's say, by scalar I mean numbers. So let's say one scalar is K, another scalar is L, and A is our matrix. So K and L belongs to the complex number in general. And this will be equals to L, K, A. That means if you first multiply L with the matrix A and then multiply K, the result will be similar as when you multiply K with the matrix A and then multiply L with it. Again, this is easy proof. We work in the component notation again, or the index notation, whatever you want to call it. So remember, this K and L's are number, right? They belong to the, in general, they belong to the set of complex numbers. So we want to write like this, and you can see that these numbers, they are like this. At this point all of them are numbers, but these two numbers, but multiplication of complex numbers is also commutative. So that means the order doesn't matter. So you can write LK and IJ, and from here you can again give a bracket, sorry, IJ, yeah, and finally you can write A. That is from the component notation, and then you can just get rid of these components. So this is a very easy proof again. And the final property that we will be looking at is the following. You have two scalars K plus two scalars K and L. If you add them and multiply by a matrix like this, and you have Ka plus La. I believe this is called the distributive property. And this is easily proven again using the index notation. So in this lecture we looked at some properties of matrices, and to be precise, we talked about properties of matrix addition and scalar multiplication. Oops. So this will be all for today, and I'll see you guys in the next lecture. Thank you.